Right, we're going to introduce mappings between fields, which will be a fundamental concept in what follows. So we're going to start with a field homomorphism, and throughout all of our fields are going to be subfields of C. So you'll see that everywhere, although it's not required. Nothing that I'm going to say is special to being subfields of C, unless I say otherwise. So suppose K and L, again, are subfields of C, but it's not important. That part's not important. A field homomorphism or just a homomorphism for short, it's implied by the fact that they're fields, is a function phi from K to L such that phi is compatible with the addition, that is, it breaks up under addition, and phi is compatible, let me put it as a second bullet, it's compatible with the multiplication. So it breaks up under multiplication for all x, y that are inputs, and the inputs belong to K. All right, so that's what a homomorphism is. If phi is 1-to-1, which is actually always true when the domain is a field. So sometimes field homomorphism is not even used, it's just a monomorphism. So this is, again, automatic when K is a field, which it is in this problem. But if in general, if you have a mapping of rings, you have to check it. But when the domain is a field, it's automatic. It's called a monomorphism. All field homomorphisms are monomorphisms. Remember that. If it's also onto, well, it's automatically 1-to-1, and if it's also onto, sometimes onto is called being an epimorphism, but you're always already 1-to-1. So if phi is in addition onto, then phi is what's called an isomorphism because it's already 1-to-1. So in addition to those, if phi is an isomorphism and K equals L, so the domain and codomain are the same, then phi is called an automorphism. So a self-isomorphism, an isomorphism to the self. Okay, again, all field homomorphisms are automatically monomorphism. It means the same thing. If you're also onto, you're an isomorphism. And if the domain and codomain are the same thing, so you're mapping to yourself, and you're an isomorphism, you're called an automorphism. All right, let's do a quick proof. Of some results that we can get from this. So this is proposition 1.4 in your book. And it's just going to tell us that certain properties and certain elements are preserved by field monomorphisms, which again is just a homomorphism. So phi from K to L is a monomorphism. That is, it breaks up under addition and multiplication. Then the following are true. Phi of 0 is 0. Let's call that A. So it preserves 0. Phi of 1 is 1. It preserves 1. So it preserves the identities, the additive and the multiplicative identities. Phi of negative x is negative phi of x. Phi of x to the negative 1 is phi of x to the negative 1 for non-zero x's. So it preserves inverses. Okay. So we get that. Remember, K and L are fields. We get that just from the definition. Proof. Well, we know let's start with A. We know 0 plus 0 is 0. Great. Brilliant. So phi of 0 plus phi of 0, oops, jumped ahead for a second. Phi of 0 plus 0 is phi of 0. Why? Well, it's the same input, so of course the output has to be the same. But the left-hand side we can rewrite using compatibility with addition. So phi compatible with plus, as phi of 0 plus phi of 0 is phi of 0. And then we can subtract phi of 0 from both sides. Phi of 0 is therefore 0. Cool. All right. So it preserves the additive identity. And now let's show it preserves the multiplicative identity. We know that, well, 0 plus 0 was 0. 1 times 1 is also 1. So phi of 1 times 1 is phi of 1. And phi of 1 times phi of 1 is phi of 1. But phi of 1 is not 0, as phi is 1 to 1. And we already know that phi of 0 is 0 by part A. So phi of 1 can't also be 0, otherwise it would fail to be 1 to 1. So phi of 1 inverse, oops, exists. And so we can multiply both sides by phi of 1 inverse. Scroll down quite a bit. All right, this guy, these guys, I'm just going to do in red. These ones cancel, and we're going to get phi of 1 is 1. Fantastic. So phi preserves the multiplicative identity. Alternatively, you know, we have phi of 1 squared minus phi of 1 is 0. Right, if we were to move that over. And really, if we want to start thinking kind of like in a... this class is largely about zeros of polynomials, so if we want to think about from a polynomial point of view, we're looking at the polynomial t squared minus t is 0. And that has two options. It's t is 0 or t minus 1 is 0. Okay, so phi of 1 is either 0 or phi of 1 is 1. Those are the options. That's another way of doing it. That's how your book does it. Okay, so let me put that in a bubble. And I'll let you look at the book for how that proceeds. Or figure it out yourself. C, all right, I forgot what C was. Let's look at it real quick. It preserves additive inverses. Well, we know that x plus negative x is 0. So phi of x plus negative x is phi of 0. But we computed phi of 0 is 0. And this breaks up, left-hand side breaks up under addition. So we can write it like that. And then we could subtract phi of x from both sides. I guess we're not done yet. And then the last one is that it if 0 is not x, then x inverse exists in K because it's a field. And what is the defining property of x inverse? Well, x inverse times x is 1. Let me scroll down a little bit here. So phi of x inverse times x is phi of 1. Phi is compatible with multiplication, so we can break this up under multiplication on the left. And in part B, we proved that phi of 1 was 1. But again, phi of x is non-zero because x is non-zero and phi is 1 to 1. So we can divide by phi of x. So we're going to multiply both sides by phi of x inverse. That's what it means to divide by phi of x. And if we do that, oops, these guys become 1. And we get exactly what we wanted to show.